All right. If you notice we skipped 6.1, don't worry, we're going to come back to that. Okay. It's something called slope fields, but we'll come back to that. What we're going to do now is we're going to move on to a lot of taking the antiderivative and all the techniques that are involved with it. The main one that we're going to go through is substitution today. So, but first we're going to introduce you to something here called the indefinite integral. All right, the indefinite integral, it is the family of all antiderivatives of a function. Okay, it's called the indefinite integral. It's denoted by this. Notice how this is different than the definite integral. The definite integral had limits of integration to it. This one has no numbers that go with it. Okay, and so, excuse me, when I want to find, if I'm given that the derivative of the antiderivative is equal to my f of x, then the antiderivative of f of x is equal to capital F of x plus a constant. Okay, does that make sense? Because if I take the derivative of anything, right, if I take this derivative, okay, and I add on any number to it, it doesn't matter what it is, right? For instance, okay, let's say that I say that big F prime of x, which is equal to f of x, is equal to x. All right, and then so I want to say then the integral of f of x dx. Well, what function, when I take the derivative, gives me x? Well, that's going to be x squared over 2. And hopefully when you take the derivative, you can see, well, yes, that's going to give me just x as a derivative. But I can have any number I want here. That's why I put a plus c. So my capital F of x is equal to x squared over 2. But I can have any number attached to that. I have plus a 4, plus a 3, plus a 2. Why? When I take the derivative of this, that number goes to 0 and it goes away. Another interesting thing of note is this down here, I want you to get here, is that an indefinite integral is a family of functions having a common derivative. If the fundamental theorem of calculus that we just got done talking about had not been provided such a dramatic link, okay, between the derivatives and the antiderivatives, okay, and the integration part of it, of finding the area underneath the curve, there wasn't that link that was there, okay, we would be having some different type of notation here. But they are two different types of functions or two different types of things that we need to keep separate. Okay, so we need to be thinking, when we see the limits of integration there, we need to be thinking about area between the x-axis, and we need to be thinking about positive area and area below the curve. And we don't have those limits of integration, we need to be thinking about the antiderivative. What is, I need to think of it as that c, that something plus a c. All right? So let's go see what's next. So to see how this is used, I want to evaluate this. So I again want to be asking myself two separate questions. First, what function, when I take the derivative, is going to give me x squared? So I've tried to explain this to a couple of people, okay? But when we take the derivative, so if I gave you initially, let's say x to the 5th, let's say 2x to the 5th, and I want to take the derivative, okay, well, what do? I multiply to get 10, and then I subtract 1 to get to the 4th. Well, to do the antiderivative, we do the opposite, in the opposite order. So here we multiplied and then subtracted, so we're going to go backwards. We're going to add and then divide by our new number. And that's how we handle power rule ones. We add and then divide. All right. And then what function, when we take the derivative, gives me negative sign? Yes, you do need to know these. So that's going to be a positive cosine of x. Well, I'm not quite done yet. Remember, this is the whole family of functions, not just this particular one. So I need to make sure that I add this plus c. I always have to have that constant of integration. All right? In fact, it's so important. Must have. Okay? Don't forget the plus c. Here we go. Next. Whoa! These are all your rules. All right? They're basically telling you the backwards ones. Okay? Properties of indefinite integrals. We've already seen these with properties of definite integrals. Those still hold. Okay? The power formula, right? Add one, divide by it. Okay? Trigonometric ones. Okay? Cosine becomes sine. Okay? Sine becomes negative cosine. All these ones. Exponential and logarithmic ones. Okay? I give you all of those there. Okay? You need to know these. All right? Mostly easy because it's just going backwards. So it's use them. Almost. Because one more thing we have to do is we have to pay attention to the differential. What's the differential? That's a differential. That's a differential. That's a differential. We must pay attention to what's there. And this makes a huge difference to when we integrate or do the integral. Okay? Take the antiderivative. So when I do, let's take a look at the first one. The first one says the integral of, or the antiderivative of, just plain old f of x dx. So, here we go. It's the integral of x cubed plus 1 dx. I match up. Does my differential match up to here? Yes. So now I can take the antiderivative. My differential matches up to the variable that's inside the integrand. Great. So now I say this is x to the fourth divided by 4 plus an x plus a c. Ta-da! We're all done for part A. But what about part B? Alright, so f of u. So now I take u and input it into there, into f. So now I have the integral of u cubed plus 1 du. And does my differential match up to my integrand? Yes. So again, I take the derivative the same way, or antiderivative the same way, u to the fourth over 4 plus a u plus a c. But now I also want to put this back in terms of x because they tell me that u is equal to x squared. So when I go ahead and replug into here, all right, it's x squared to the fourth over 4 plus x squared plus a c. And then I go ahead and multiply everything. This is x to the eighth, 4 plus x squared plus a c. And that takes care of the b. There's my answer. Again, I repeat the same process for part C. So part C, I go, well, it's the integral f of u. Okay, well, that's just u cubed plus 1. Now it says dx. Now I ask myself the same question. Does my differential match up to my integrand? No. So I need to make it match up. So they say u is equal to x squared. Okay, so that means u is now going to be x squared to the cube plus 1 dx, which is equal to integral of x to the 6 plus 1 dx. Now again, I ask myself, I'm at a spot, hey, my differential does now match up to my integrand. So now I'm able to take the antiderivative. And when I do, this becomes add 1, divide by the new number, plus an x, plus a c, and there I'm done. as you can see, the answer that we got in part C does not match up to the answer that we got in part B. It is very important that your differential match up to your integrand. They are not going to be the same answer. Why did I go through this whole example? Because of what's coming up next. What's next? Oh God, that looks horrible. Okay, so the antiderivative of sine x e to the cosine x. Oh. Well, I got an idea. Let's go check our rules. Okay, so I go back here. I'm going to check my rules. Sine x e cosine x. I don't have anything like that. I have sine x and I have e to the u, but nothing exactly like that. Well, what can I do? So what we're going to do is we're going to make up a u, and I'm going to just lead you through this one. All right, I'm going to make up what's called a U-substitution. So I'm going to use substitution. I'm going to say u is going to equal cosine of x. Great! So I go back in here and I plug all that in. Sine of x will e, all right, to the u dx. Great. Oh no. I take a look at my differential. Does it match everything in my integrand? No. Well, how can I get a dx? This goes back to that idea of, remember when I told you that if I have a derivative of u du dx, never to treat it like a fraction unless it's convenient. Convenient. Okay. So what we're going to do is to take the derivative with respect to x, or du dx, over here is going to be equal derivative of cosine. Oh, that's negative sine of x. Well, it's getting a little bit better, but I want to make dx all by itself here, so I want to get du is equal to negative sine of x dx. Well, why is that promising? Let's take a look. If I rewrite this, right, and I come over here, this is the integral of e to the u sine x times dx. Oh, look, this is really close. Look, I can substitute almost again. Look how close that is. Only difference is this negative. Oh, well, I can go ahead and multiply by a negative 1 on both sides, so negative 1, right, du is equal to sine x dx. So now I can go ahead and take that and substitute negative 1 du for it. Oh, okay. E to the u times negative 1 du. Oh, well, what can I do with the negative 1? Well, my rules say is that I can take this negative 1 and put it on the outside. Integral of e to the u du. Now I ask myself, does my differential match up with my integrand? You bet it does. So now what can I do? Well, now I have the rule, and I can go look back at those rules. And I go and I look back at those rules. I'm cheating, I already know. And I say, well, this is negative 1 times, well, e to the u plus c. I multiply everything, and what's u though? Because I want everything back in terms of x, because that's what I started. Well, it's negative 1 e to the cosine of x plus a c. Now I can go ahead and multiply by that negative 1, negative e the cosine of x. Now this is where you're going to yell at me, because I'm going to write down plus c. You're going, but mister, I just multiplied by a negative 1. Shouldn't it be minus a c? And this is where I'm going to come back and say, look, the whole idea of taking an antiderivative is coming up with a family of functions, which this is, and coming up with saying, there's my family of functions. Does it really matter what c is? It's a number. Doesn't matter if it's a negative c or a positive c. Why? Because when I take a derivative of a negative number or a positive number, it gets to be the same thing, 0. So it doesn't matter what I do to c. It will always just be plus c, because it's always just a number. That's its whole sole job is to be taken the derivative of and made into 0. Okay? But it's important that it's there. Therefore, there's my answer. I do a little happy dance and call it a day. I see what's next. So when we get to these, it comes down to, well, how can I choose which one to use? What can I choose to make my, which one's going to be my U-substitution? And generally what I'm going to say, it just takes practice to see it, guys. The practice is going to pay off. You need to keep up with the homework on this one, okay? Generally speaking, what you want to try and do is you want to try and take something that looks complicated and make it simple. So from my point of view, when I look at this, what's the most complicated? 5 plus 2x cubed, okay? And I'm not going to take the square root part, okay? Why? That's the practice part. Because what I notice here is, again, you have to know what's going to happen. If I say u is equal to 5 plus 2x cubed, and I go in and I substitute right away, I have now integral x squared square root of u dx. Again, my differential does not match up with all my variables that are in here. So what can I do? Again, I take the derivative. And again, the experience part tells me when I take the derivative, du dx, what's going to happen here? Well, I'll take the derivative of 5, 0, 2x cubed. Oh, well, derivative is going to be 6x squared. And then I can go ahead and multiply by a dx. And I said du is equal to 6x squared dx. And look, I'm getting super close to what I want. X squared dx, right? Because I rearranged this, okay, over u times x squared dx. I'm almost there, the x squared dx, so I can divide by 6. I get 1/6 du is equal to x squared dx. Well, again, I match this up. I go, wow, I can replace those. And when I replace those, what I'm going to say is the 1/6 I already know is going to come out integral. Instead of saying square root of u, I'm going to write u to the 1/2 power. And instead of writing x squared dx, I'm going to write the du. And notice the 1/6 du is still there. It's okay. And now I know how to take the derivative of this. Okay. U to the 1/2, so this is going to be 1/6 times antiderivative of u to the 1/2, add 1. So it's 3/2. Divide by the new 3/2 plus a c. Well, dividing by the 3/2 is the same thing as multiplying by 2/3, and I replace my u. So now I have 1/6 times 2/3. The u is going to be 5 plus 2x cubed to the 3/2 plus a c. And I can multiply the 1/6 and the 2/3 together, and the 1/6 and the c. And what I get is 2 over 18, or 1/9. That's 1/9. 5 plus 2x cubed to the 3/2 plus a c. Again, I know you're going to say, but wait, mister, it's c times 1/6. That's going to make a difference. Well, does it? I mean, it's still going to be a number, right? And what I'm coming up with is a family of functions that when I take the derivative, I get my answer. And so when I take the derivative of this, I'm going to get the x squared square root of 5 plus 2x cubed. it doesn't matter what the C is. Trust me. Okay? There we go. I got one more example for you to do on your own. Okay? And I made a mistake when I put this up there. This should be 5x squared minus the 1. So make that change, solve the problem, and see if you get the same answer. Bada boom, there it is. Take a moment to pause me and see if you can follow all the steps. Okay? Make sure you got this. Okay? Because here's your homework. Okay? Again, Canon up at the top. It's actually labeled 6.2 Canon, 6.2 Larson on yours. Okay? Those are different books, different handouts that you guys picked up, I guess, when you picked up the stuff. All right? Good luck. I'm expecting questions tomorrow because this is not going to be something that's going to be straightforward and easy. All right. Peace out.